Okay, for this video, I'll be going through Pure Physics, Electromagnetism, Chapter 18, Success Criteria E and F. Okay, so basically, what we have covered so far is when current flows, okay, when current flows, it will produce a magnetic field around it, okay. So in the presence of an external magnetic field, okay, if there is an external magnetic field around it, okay, then due to the interactions of the magnetic fields, okay, so there are actually two magnetic fields, okay, minimally. So let's say this is the first magnetic field produced by a current. Okay, then the second one is when there is an external magnetic field, be it a magnet being around or another current carrying conductor. So there must basically be two magnetic fields, and when they interact, then there will be a force. There will be a force produced. Okay, so we can actually find out how what is the direction of the force. If let's say we are focusing on this current flowing in a conductor, okay, so we are interested to find out what is the direction of the force on this conductor. There are two ways to go about it. The first one is actually to examine the interactions of the magnetic fields. So if they are in the same direction, okay, then they will reinforce one another. But if they are in the opposite direction, then they will cancel out each other. And the direction of the force will then be from more magnetic field lines, to less field lines. Okay, so you might want to take a look at the previous videos if you have forgotten. So this is the first method. The second method is by using Fleming left-hand rule. Okay, so you can also look at the previous videos. So we see that whenever there are interactions of magnetic fields, then there will be a force produced. So how do we actually make use of this force? So then they thought of this thing called a DC motor, right? So what is a DC motor? It consists of a coil of wire that carries current into a magnetic field. So this is our external magnetic field. So the field lines go from north to south. So if I want to just use Fleming left-hand rule very quickly, then my first finger will be pointing to the right of the screen. Okay, and because it is now shaped as a coil of wire, the current in this example is going from A to B, okay, and then coming out from C to D. Okay, coming out from C to D. So just test yourself if you know the direction of the force on AB and on the force of CD. I'm going to use AB as an example. So I can actually convert it into a 2D diagram. So this is my north and this is my south. And if I were to look at the coil or the motor in this direction, okay, in this direction, I will actually not see AB, because this is a 3D diagram. I will not see AB as the lengthwise. I will only see AB as a circle, which actually is the cross-section area of AB. And I would also see CD as a circle, which is the cross-sectional area of the wire's segment CD. And we have the direction of the current in AB to be into the page. So if I'm looking from here, it will be a cross. And for CD, it will be a dot, because the direction of the current is coming towards me, as you can see from here. So let us now apply a Fleming left-hand rule. You find that it's easier when you're actually able to convert it into a 2D diagram. Okay, so I will have my first finger pointing to the right. Okay, because the direction of the external magnetic field is from north to south, is going from left to the right. So my first finger is actually pointing to the right of the screen. Okay, to the right of the screen. And yeah, and if I'm doing AB, I then need to rotate my middle finger such that now my middle finger, which represents the direction of the current, is into the screen. Because for AB side, right, we are using a cross to show the direction of the current that is into the page. So now my middle finger is pointing to the screen, and my first finger is pointing to the right. Therefore, my thumb on my left hand naturally points down to the bottom. Okay, so if the direction of the current is reversed, naturally the force is reversed as well. And because now we shape it into the coil, okay, this thing will actually now have a moment, because this is the center of the coil, so it will actually be turning in a anti-clockwise direction. Okay, so that's how they come up with the design of this motor. Okay, but then maybe before we continue, you can also take a look at this diagram, okay, whereby they are showing the direction of the force by examining the magnetic field lines. Okay, so if they reinforce, they will have more field lines. If they are in opposite direction, then they will cancel each other out. Then there will be lesser field lines in that region. So the magnetic field lines, the force is always from more magnetic field lines to less magnetic field lines. Okay, so these are the method 1 and 2. You can read about it. Then something very important here is this split ring commutator. Okay, sometimes we just call it split ring, but it's a split ring commutator. And we also have this additional part called a carbon brush. So the carbon brush is actually a conductor, right? And it helps to conduct the current that comes out from the battery, because we are supplying the current so as to produce a force. So the carbon brush for a DC motor, okay, if they are connected this way, with the battery here being positive, so this will be the positive terminal. So the carbon brush will not change the polarity, or whether is it positive or negative, after you have connected the battery. So on this side it will be negative, right? So this carbon brush is negative. How about the split ring commutator? The split ring commutator, I can say that this is the split ring commutator of side AB. And this is the split ring commutator of side CD. Okay, they belong to individual side. Okay, maybe I should use this as a blue in color. Okay, so this is the split ring commutator of AB. Right now, the split ring commutator of AB touches the carbon brush. That is why the current flows inwards towards AB. And right now, the split ring commutator of CD actually touches the negative carbon brush. That is why the current comes out from there. Okay, and as the coil rotates, the split ring will rotate together with it as well. So why is it called split ring? Because there's this part that is separated. Okay, because later on there will be a point whereby the split ring doesn't touch the carbon brush. Okay, so if I were to look at this is the carbon brush. There will be an instance whereby the carbon brush doesn't touch the split ring. So when this happens, right, the coil will just continue to turn. Okay, it will continue to turn due to momentum or inertia, right? So the idea is to get the motor to continue turning, but when it doesn't touch the carbon brushes, there will be no current flowing through the coil, And when there's no current, then there will be no magnetic field produced by the current. Then there will be no more interactions between the magnetic field, and then there won't be a force, and there won't be a moment. So by right, the coil should stop. But because of momentum, it will continue to turn past the vertical position. Okay, so something like a fan in school, when you turn off the fan, okay, you off the switch, the fan do not come to a stop immediately. It will still continue to turn because they have momentum, or they are due to inertia. It will continue to move in the same direction. Okay, and one thing to take note is that after the after the split ring turns, right, they will actually switch polarity. Right now, split ring AB is touching the positive. But after turning, for a while, it will then come into contact with the negative terminal. And similarly for the split ring of CD, currently, as shown in this diagram, it is touching the negative side. But after turning for maybe half a revolution, it will then touch the positive terminal. Okay, so this is for the purpose of over here. The split ring commutators are used to reverse the direction of the current in the coil after half a turn, which is after 180 degrees, so that the coil can rotate in the same direction. Okay, it may sound very confusing now because I don't have anything to show you, but I have attached a link in Google Classroom whereby a video would show through animation how it actually works. Okay, so this is important. So a popular questions that they like to ask is, what is the function of the split ring commutator? So you have to memorize this. Okay, and what is the purpose or the function of the carbon brush? Is to provide contact. So I say again, the carbon brush will not change the polarity. It will either be positive or negative once your batteries are fixed. It is the carbon brushes that is touching the carbon brushes that's positive and negative alternately. Okay, so currently right now AB is touching the positive side, and can you imagine after half a revolution, AB will now be on this side, so this becomes AB. AB will then be touching the negative side of the battery. Okay, so this is so that the coil will continue to turn in the same direction. Okay, there's also a rheostat so as to control the amount of current flowing, so that we can control the speed of rotation. Okay, now take note, if the direction of the battery is reversed, the coil will rotate in opposite direction. Similarly, if we change the north and south of the magnets, the coil will also rotate in opposite direction. So how can we increase the turning effect of the electric motor? So increase the number of turns in the coil. Please do not write increase the number of coil, is the number of turns in the coil. Increasing the current, of course, and adding a soft iron cylinder. Okay, so what's the purpose of adding a soft iron cylinder into the core? Because the soft iron we have covered in previous parts, that is able to concentrate the magnetic field lines. Okay, so this part is talking about maintaining the continuous rotation. You can read through it or you can watch the video. Okay, so this is other examples of electromagnetism. This is when a charged particle is flowing in a magnetic field. Okay, it's moving in a magnetic field. So this you can apply Fleming's left hand rule. So just take note of the negative. So if it's negative, if the negative is moving to the right, okay, then the current is to the left. Okay, so that is how you need to position your middle finger, which represents the direction of the current. So this is a popular kind of MCQ question. We also talk about a circuit breaker, right? And the keyword is it must become stronger electromagnet when the current exceeds the working current value. We can also use this in a magnetic relay, whereby we have battery that is of low EMF, okay, and it becomes an electromagnet through here, so that it can activate the second switch, which is connected to high voltage. So we are using a low voltage circuit to control another switch in a high voltage circuit. You wouldn't want to be controlling or touching the switch of a high voltage circuit, so we use a low voltage circuit. Okay, then also electric bell, okay, whereby when the switch is turned on and current flows, it will attract this soft iron armature, right? So when it gets attracted to it, it strikes the gong, but at the same time it then breaks the contact and the spring pulls it back, and this thing repeats over all over again. Okay, so please watch the video that's also attached in your Google Classroom for the split ring commutator.